In the second part of the video for chapter 21 electric current, I will discuss the use of Ohm's law for analysis of the two simple types of electric circuits, the series circuit and the parallel circuit. I will also discuss electric power and electric energy. There are two types of electric circuits based on the kind of connection of the loads of the circuit to the source of potential difference. We have series circuits and we also have parallel circuits. The differences between the two types of circuits are the manner in which the loads in the circuit are connected to the power source. From now on, we will refer to the term load in a circuit as a resistor in a circuit. Each load is a device, most generally speaking, that has a certain resistance to the flow of current. And so instead of talking about loads, we are going to again talk about resistors. So from now on, the word load will be replaced by the word resistor. The simplest example of this idea for the swap of terms is the electric bulb with the filament. When the electric current passes through the filament of the bulb, the resistance of the filament itself causes the heating of the filament, which results in emission of light. So the analogy with other devices that are loads in a circuit is that they also have a certain amount of resistance to the electric current that flows through them. This makes it much easier to schematically represent loads in a circuit by simply replacing them with resistors with a certain resistance. Before I talk about the analysis of electric circuits, of series or parallel circuits, let's introduce the symbols that will be used for representing a circuit schematically. Here is an example of an actual real electric circuit where we have the power source, which is a battery, we have the conductors or the wires, we have the load, which is a light bulb, and then we have a switch that opens and closes the electric circuit. This is an example of an extremely simple circuit which has one power source and one load. However, most circuits are much more complicated than the one that is shown here, and so drawing them realistically with the elements that they contain is not practical at all, especially for circuits that include hundreds or thousands of elements. Therefore, it's more convenient to introduce a schematic representation of the different components of a circuit, which then make it much easier to draw any circuit that we would like to analyze. For the power source, we are going to use this symbol. It consists of two parallel lines with different lengths. The longer of the two lines corresponds to the positive terminal of the power source, and the shorter line corresponds to the negative terminal of the power source. And next to the power source, where applicable, the actual value for the potential difference between the two terminals is stated. So for a 1.5 volt battery, if that was it, then we'll have 1.5 volts here. If it was a 9 volt battery, then we'll have 9 volts stated here, and so on and so forth. Schematically, a conductor or a wire can be represented with a straight line, and the direction of the current flow in the wire is represented with an arrow. And finally, any load we are going to represent with a resistor, which has this schematic representation. The value of the resistance of the resistor may be listed in ohms, and of course, if it's necessary to find that value, then there will be no assigned value to that resistor. So these are the three basic elements that are used to schematically represent circuits. Circuit analysis is based on several simple points. First, the use of Ohm's law, which relates the potential difference between the terminals of a power source or between any 2 points in the circuit, the current in the circuit, and the resistance of the circuit. And then the analysis also is based on a set of rules about the current, the potential difference, and the resistance in a circuit. And these rules are characteristic for each kind of circuit. So when I do the analysis of series and parallel circuits, I will explain what these specific rules for the current, the potential difference, and the resistance are, and also how the Ohm's law is applied in analysis of each type of circuit. A series circuit is a circuit in which the resistors are connected one after the other in series, as shown below. So in this circuit, we have the power source, which can be, again, a battery or the power grid or any other source of potential difference in the circuit. The first resistor, R1, is connected to the power source with one of its ends, and then the other end is connected to a second resistor, R2. The free end of R2 is connected to one of the ends of resistor R3. The free end of R3 is connected to a fourth resistor, R4. And then the free end of R4 is connected to a resistor R5, which on its turn is connected to the negative terminal of the power source. The direction of the flow of the electric current is presented with an arrow, and that is the current that the power source supplies to the circuit. Now, this particular example is an example of 5 resistors connected in the circuit in series, but of course we can even have 2 or 1,000 resistors, as long as the rule of connection is just like I explained it, then the circuit will be a series circuit. The current that the power source applies to the circuit, I'm going to refer to as I total, while the current in each of the resistors I will refer to as I1, I2, I3, I4, I5 in this particular circuit, and then depending on how many resistors you actually have in a series circuit, that will also tell you how many individual currents you have based on the number of resistors. So we have 2 main types of currents here. We have the total current in the entire circuit that is supplied by the power source, and then we have the current in each individual resistor, and these currents are indexed with the number of the resistor in the circuit. And here is the first rule for a series circuit, and this is the rule for the currents in a series circuit. In a series circuit, the total current is equal to the current in each resistor. Or in other words, the current supplied to the circuit by the power source is equal to the current in resistor R1, is equal to the current in resistor R2, is equal to the current in resistor R3, and so on and so forth for however many resistors there are in that series circuit. When we consider the power source of a circuit, we note that there is a potential difference between the 2 terminals of the power source. The terminal that is with the positive sign has higher potential value than the terminal with the negative sign. So then if I start going around the circuit in a clockwise direction, passing through the resistors in order, R1, R2, R3, R4, and I5, the potential difference between that end of the first resistor and that end of the first resistor will be non-zero. And this is because this resistor has a certain amount of resistance and a certain current passes through that resistor. Now, moving on to resistor number 2 with resistance R2, the potential difference between the 2 ends of that resistor will be also non-zero, but because the values here of those 2 resistors are in general different, the potential difference between the 2 terminals of that resistor will be different than the potential difference between the terminals of resistor number 1. Then the potential difference between the terminals of resistor number 3 will be different than the potential difference for resistors number 2 and number 1. And the same applies for resistors number 4 and number 5 compared to the other resistors in the circuit. So then, what is the relationship between the potential difference supplied to the circuit by the power source and the potential differences for each of the resistors? Let's call the potential differences for each resistor V1, V2, V3, V4, and V5 respectively. So here is the next rule, and that is the rule for the potential difference in a circuit. The potential difference between the terminals of the source, which we will call the voltage in the circuit, is equal to the sum of potential differences, or as we will term them, voltage drops of the resistors in the circuit. Or in other words, V is equal to V1 plus V2 plus V3 plus V4 plus V5 plus, and if we have more resistors, you just keep on adding the voltage drops for each resistor. So again, the voltage in the circuit, which is supplied by the power source, is equal to the sum of the voltage drops in each resistor. So we have our series circuit. The power source applies voltage V to the circuit. We have a total current I total that the power source injects into the circuit. What is the relationship between the voltage that the power source supplies to the circuit and the total current in the circuit? Before we can answer that question, let's talk about the total resistance of the circuit. It is possible to find one resistor that has its resistance has the same effect as the resistances of all these 4 resistors for the entire circuit. If I replace those 5 resistors with that one resistor that has resistance that's equivalent to the resistances of those 5 resistors, then the operation of the circuit will not change. We still will have the same amount of voltage supplied to the circuit by the power source, and still will have the same amount of total current in the circuit. So then I can replace this series circuit with a circuit that looks like that. And here we have the total current flowing in the circuit. So then now I can use Ohm's law to write down the relationship between the voltage in the circuit, the total current, and the total resistance of the circuit. And Ohm's law, we know, looks like so. V is equal to I total times R total. Now the question here only remains, what is the total resistance of the circuit? So again, keep in mind that this total resistance replaces those resistors, the resistances of those resistors here. So that is our third rule for series circuits. The rule reads that the total resistance of a series circuit is calculated as the sum of resistances of the individual resistors of the circuit. Or in other words, R total is equal to R1 plus R2 plus R3 plus R4 plus R5, and this is for our specific circuit. And then if there are more resistors, you just keep on adding them like that. If there are less resistors, you just add the resistances of the resistors that are present in the circuit. Let's quickly also list Ohm's law for the individual resistors of a series circuit. So far I talked about the rules that govern the relationship between the voltage supplied to the circuit by the power source and the voltage drops for each resistor. Also, the rule for the current the total current in the circuit and the currents in the individual resistors, and also the total resistance of a circuit and the resistances of the individual resistors. However, I did not talk about the Ohm's law application for each of the resistors separately. The Ohm's law for each of the resistors separately is really straightforward. For the first resistor in the circuit, the voltage drop V1 is equal to the current in that resistor R1 times the resistance of the resistor R1. For the second resistor, we have V2 is equal to I2 times R2. For the third resistor, we have V3 is equal to I3 times R3. And so on and so forth for the other two resistors. Or if there are more resistors, you just keep on writing down the Ohm's law indexed for each resistor. If there are less resistors than the 5 that I have in that example circuit, then obviously you will have only the Ohm's law for the number of resistors present. So combining the rules for the entire circuit, for the voltage supplied to the circuit, the total current and the total resistance, with the rules for the individual, with Ohm's law for the individual resistors, allows you to find all the information necessary to analyze a simple series circuit. Now let's do a few examples involving series circuits and Ohm's law. First, let's find out what is the resistance of a light bulb that draws 0.5 amps when it's plugged into a 120 volt outlet. So let's make a list of the information that we know from the statement of the problem. We know that the current that passes through the light bulb is 0.5 amps. The voltage supplied to the circuit where the bulb is plugged in is 120 volts. And the resistance of the bulb is what we want to find. If you were to draw this as a simple circuit, that would be something like this. So we have the power source here, which is 120 volts. We have the current in the light bulb, which is 0.5 amps. And the light bulb has some resistance R that we want to find out what it is. So the current, the voltage, and the resistance are related through Ohm's law, which states that V is equal to I times R. And from here, R is equal to V divided by I. That gives us 120 volts divided by 0.5 amps, which gives us 240 ohms. So that is the resistance of this light bulb. Here is another example. Two 3 ohm resistors are connected in series to a battery. What's the equivalent resistance of those resistors? Since those resistors are connected in series, we know that the total resistance for series connection is equal to the sum of the resistances of the individual resistors. Since we have only 2 resistors here, then that is the sum of the 2 resistances of those resistors. So this is 3 ohms plus 3 ohms, which gives us 6 ohms. Let's do one more example. A 2 ohm and a 4 ohm resistors are connected in series to a 12 volt battery. First, what is the current in each resistor? And second, what is the voltage drop across each resistor? Well, let's draw the circuit that represents the statement of the problem. Here is my power source, a 12 volt battery. Here is resistor number 1 with 2 ohms resistance and resistor number 2 with 4 ohms resistor. I want to make a note here that the way I drew the circuit is completely random, meaning that I can place the second resistor on the same wire as the first resistor, or I can place that second resistor right here instead of here. It doesn't matter, it's still the same circuit. Nothing will change as far as currents are concerned, and so on and so forth. So part A of the question is asking us what are the currents in each of the resistors, so I1 and I2. In order to find the current in each resistor, I need to go back to the rules that I set for the currents in a series circuit. And the rule says that the total current in the circuit is equal to the currents in each of the resistors. So then I have two possible ways to go about it, one of which is not going to give me a result. So what is this one way that is not going to work to solve the problem? That would be to use Ohm's law for the individual resistors. This is not going to work because I don't know what the voltage drops are for each resistor. So then the other way to go about solving the problem, which will give me a result, is to determine the total current in the circuit. I can find the total current in the circuit because I know the voltage supplied by the battery, and I also can calculate the total resistance of the circuit using the resistances of those two resistors. So to solve the problem, I'm going to use Ohm's law for the entire circuit. So V is equal to I total times R total. Since this is a series connection of resistors, the total resistance is simply the sum of the two resistances. So this is equal to 2 ohms plus 4 ohms, and this is equal to 6 ohms. Now I can find the total current in the circuit by dividing the voltage supplied by the battery by the total resistance. So this is 12 volts divided by 6 ohms. That is going to give me a current of 2 amps as the total current in the circuit. Now, remember one more time that according to the rules for series connections, the total current is equal to the currents in each of the resistors. So that means that I1 is equal to I2 is equal to 2 amps. For part B, I must find the voltage drops for each of the resistors. So we want V1 and V2. In order to find those, I'm going to use Ohm's law for each resistor individually. For resistor number 1, V1 is equal to I1 times R1, which gives me 2 amps times 2 ohms, so this is 4 volts. For resistor number 2, V2 is equal to I2 times R2, and this is 2 amps times 4 ohms, so this is equal to 8 volts. We also know, as a check, that from the rules for series circuits, the voltage supplied to the circuit by the power source must be equal to the sum of voltage drops for each resistor. So 4 volts plus 8 volts is equal to 12 volts, and this is what we get in the circuit from the power source according to the statement of the problem. So the check confirms that the two results here are correct. Now let's discuss the set of rules for the voltage, the currents, and the resistance of a parallel circuit. In a parallel circuit, the resistors are connected so that one of the terminals of each resistor is connected to the positive terminal of the power source, and the other terminal is connected to the negative terminal of the power source. So here's an example of a parallel circuit. We have our power source, and then we have 3 resistors, R1, R2, and R3. We have one terminal from each resistor is connected to the positive terminal of the battery, and then we have the other terminal from each resistor connected to the negative terminal of the battery. The battery supplies a total current I total in the circuit, which goes in that direction. When the current reaches this junction right here, part of it is going to flow along this branch, and how much of that current is going to go there depends on the amount of resistance in resistor R1. So the current in R1 we are going to call I1. What's left of the current here continues until it reaches that junction, where it splits again, and some of the current is going to flow through R2. So this current, let's call I2. what's left of the current is going to continue and it's going to flow through R3. So let's call this current I3. Now, since the three resistors are connected to the terminals of the battery, the potential difference or the potential drop for each resistor, I'm going to label V1, V2, and V3. But since those resistors are connected to the battery the same way, these potential differences are actually equal to the potential difference or to the voltage supplied to the circuit by the power source. And so this is my first rule. So the first rule is the rule for the voltages, which states that the voltage in a parallel circuit is equal to the voltage drops in each resistor. Or in other words, V is equal to V1, is equal to V2, is equal to V3, and so on and so forth if you have more resistors connected in a parallel circuit. Now let's see what is the rule for the currents in the circuit. As I already explained, the total current reaches this first junction and some of it will flow into that junction, and that amount is determined by the resistance of the first resistor. What's left continues towards the second junction, where some of the leftover current will flow into that junction, and again the amount depends on the size of that resistor R2. What's left will flow into the third resistor as the current I3. Then I3, getting to the top junction right here, merges with I2. The combined current flows towards this junction where it merges with I1, and then after that we have the total current flowing here towards the positive terminal of the power source. So the relationship between the total current and the individual currents is that the total current in the circuit is equal to the sum of the individual currents in the resistors. So the rule states that the total current in a parallel circuit is equal to the sum of currents in the resistors of the circuit. Or in other words, I total is equal to I1 plus I2 plus I3 plus and so on and so forth if you have more resistors. Finally, let's discuss the rule for the total resistance of a parallel circuit. I can replace the three resistors in this circuit with a single resistance with a resistance that is equivalent to the resistance of those three resistors in the circuit here. If I find such resistor and do the replacement, then the circuit that I'm going to get will be functionally exactly the same as the circuit that is shown on the board right now. So then I can schematically represent the new circuit as shown here. So this total resistance here is the resistance equivalent to those three resistances in the original circuit. I'm still going to get the same amount of total current in the circuit. And so the question is, how do I calculate this total resistance here? The rule for calculation of the total resistance for a parallel circuit is different than the rule for series circuits. And so here is the formula for calculating the total resistance for a parallel circuit. So the total resistance is equal to 1 divided by the sum of the inverses of the individual resistances of the resistors in the circuit. So for three resistors we have 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. If we have more resistors in that parallel circuit, then we just keep on adding those types of terms. As you can see, this is a very different expression compared to the total resistance for series circuits. You've got to be careful here when you're calculating the total resistance. if you are entering the entire thing in your calculator, make sure that you 1 divided by and then parentheses, and then you enter the sum like so, close the parentheses, and then you get the answer correctly. Let's do the following example. A 5 ohm and a 10 ohm resistors are connected in parallel. Find their equivalent resistance. So the value of the first resistor is 5 ohms. The value of the resistance of the second resistor is 10 ohms. According to the formula discussed before, the total resistance of the two will be 1 divided by 1 over R1 plus 1 divided by R2. So that gives me 1 divided by 1 over 5 ohms plus 1 over 10 ohms, which when you calculate it, you get 3.3 ohms. Let's do one more example. A 5 ohm resistor is connected in parallel with a 9 ohm resistor to a 12 volt battery. What is the total current in the circuit? So here is the parallel circuit. We have the 12 volt battery connected to two resistors in parallel, a 5 ohm and a 9 ohm resistor. 5 ohm and a 9 ohm resistor. What we want to find is the total current in the circuit. So in order to find the total current in the circuit, we got to use Ohm's law for the entire circuit. Ohm's law for the entire circuit says that the voltage supplied to the circuit is equal to the total current times the total resistance of the circuit. So since we don't know the total resistance, that is the thing that we need to calculate first. The total resistance for a parallel circuit, in this case, will be 1 divided by 1 over R1 plus 1 over R2, which comes out to be 1 divided by 1 over 5 ohms plus 1 divided by 9 ohms. Let's calculate that. The calculation gives us 3.2 ohms as the total resistance. So then the total current is simply the voltage supplied by the battery divided by the total resistance. So this is 12 volts divided by 3.2 ohms. That is equal to 3.75 amps. The last two items to discuss in this lecture are the concepts of electric power and electric energy. From before, we know that power is defined as the energy divided by the amount of time or the elapsed time for which this energy was transported from one place to another or absorbed and converted into a different type of energy. In our specific case, in the case of electric currents, the energy in question is the electric energy. So power is going to be defined as the electric energy consumed for a certain amount of time. So electric power is the amount of electric energy consumed divided by the elapsed time. The symbol for power is capital P, and in terms of electricity, power is calculated as the product of the current in the circuit and the voltage supplied to the circuit. Using Ohm's law and substituting V for I times R, I can get a second version of the expression for the power, and that is I squared times R. So the current in the circuit to the second power times the resistance of the circuit. As you can see, those are two expressions that can be used depending on what information is provided in the stated problem. If you have the current and the voltage in the circuit, then the first formula for power applies. If you have the current and the resistance of the circuit, then the second formula for the power applies. Finally, there is a third version of the formula for power, and that involves the voltage in the circuit and the resistance of the circuit. So the power is also equal to the voltage in the circuit to the second power divided by the resistance of the circuit. The units that are used for power would be watts, just like before. But when we are dealing with electric currents and electric power, the power values are actually pretty large, and so another very common unit is kilowatts, and we also have megawatts. Megawatts are is power that is generated in power plants, typically. And kilowatts is the power consumed by larger devices such as generators or more powerful electric appliances. Electric energy is equal to the electric power multiplied by the time of consumption. So to find the amount of electrical energy used when a certain device operates with electric power, we simply multiply the power consumption by that device and the time for which the device was operational. That gives us the electrical energy consumed. Typical units for the electrical energy would be watt-hours or kilowatt-hours. So for example, when you're paying your electric bill, you are actually paying for the amount of electrical energy consumed for a certain period of time. And typically the readings are in kilowatt-hours. And then the price of the consumed energy is calculated as the amount of energy used times the price per kilowatt hour, and that gives you the total that you are going to pay. And so with this, I'm going to finish the lecture on electric current.